We are still continuing our discussion on acids, bases, and salts. And today we are going to be talking about how to prepare acids. Remember, we have organic acids and we have inorganic acids. Organic acids, you can manufacture them in the laboratory, yes, but mostly you find them naturally. As for inorganic acids, you don't find them naturally. So what happens? They have to be synthesized. They have to be manufactured in the laboratory. So how do you make these acids? There are three main methods. Number one is just combination. Of constituent elements. As the name already says, constituents, that's the elements that make it up. You just take the elements that make up the acids, join them together, and that gives you an acid. But you are going to need to watch out for this because it does not apply to all acids. It is not all acids that you can manufacture just by combining the constituent elements. The next one is dissolving acid and hydride in water. Now, I already called this one the second one, but it is actually going to be the last one we discuss because it has some concepts that we are going to treat. I have to treat them specially, I guess. And then for the third one, it's quite like a long story, but it's the same thing. Displacing a weaker acid from its salt using a stronger acid. So these are the three main methods of manufacturing or producing acids. So let's just call it how to manufacture acids. And as you are going to see, most of the examples, if not all the examples we give today, they are all going to be inorganic acids because they're the ones that you really have to manufacture. For the organic acids, you can just basically go to their source and get what you need. So the first one, combining constituent elements. As the name already says, all you are just doing is you are taking the elements that make up the acids and you are combining them together. But what you have to take note is that it applies to binary acids. From the word binary, in mathematics, binary means base 2. So when you say binary, it means 2. So when you say, I remember talking about constituent elements, so it means that the acid has 2 constituents. And remember, in an acid, something must be present. That is hydrogen. So basically, a binary acid is an acid that contains hydrogen and one other element, a non-metal. So in some certain acids, you can simply take hydrogen, take the non-metal, join them together, and you get the acid. So we simply say combine the elements. Oh, sorry about that. Well, I guess I can take this one out. Combine the elements that make up the acid. Again, remember talking about binary acids, and I'm going to make a point under these binary acids. So now you have an example. Let's just say H plus Cl gives you HCl. Now we could have done this, and however, as chemistry students, we can't commit this kind of crime. Remember, when writing hydrogen or chlorine, they have to be diatomic. So it has to be H2 and Cl2. So when you balance the equation, you have 2HCl. So you can see, all you simply had to do was take hydrogen, take chlorine, join them together. You have combined the constituent elements. Now, what will you call this one? They are both gases in this case, so it's called hydrogen chloride. So if you want it in solution form, you dissolve it in water and it becomes hydrochloric acid. Same thing applies for others, and then you can have hydrogen combined with sulfur. That gives you hydrogen sulfide. So these are just two examples, but you can give more. So basically, pick hydrogen and pick a non-metal. That is most likely going to be an acid. But remember, I spoke of an exception in earlier videos. An exception is ammonia. Ammonia has nitrogen and hydrogen, two non-metals involving hydrogen, but that is not an acid. Why? Because remember, the definition of acid comes from their behavior in solution. So in solution, when you dissolve ammonia in water, an acid should be a proton donor. Instead, ammonia accepts protons. So automatically, it is not an acid. An acid gives off hydrogen ions, according to Arrhenius, gives off hydrogen ions in solution. Ammonia does not. So therefore, it is not an acid. So don't go around picking just any metal, any non-metal and hydrogen. You have to make sure that, yes, it behaves as an acid. And these are some confirmed ones. So you can go on, do a little research, and find out which are exceptions. An example which may sound funny is water, H2O. It contains hydrogen and it contains a non-metal oxygen. But the question becomes, is water an acid? Is water a base? Or is water neutral? I guess I'll leave you to ponder that, and let's see what you come up with. But the main idea here remains, not every time when you have hydrogen and a non-metal, not every time does it give you an acid. It has to behave as an acid when it is in solution. But a sure thing you can have is hydrogen and halogens or group 7 elements. So your fluorine, bromine, iodine, and chlorine, like we already have in our example. Those are sure examples. All right, so just before I leave here, it is good to mention, to note that all binary acids are strong acids, except hydrogen fluoride. That is a weak acid. And the reason is because of its electronegativity. Remember, what makes something a strong acid? It is the ability to ionize completely in solution. And that involves, for it to be able to ionize, that means the hydrogen has to split away from the whatever it is combined with. In others, it is able to split and leave completely, 100%. But in hydrogen fluoride, remember, this will now have hydrogen bonding. Due to the nature of the bonding, it is very difficult for the hydrogen to leave the fluorine. They have a strong intermolecular force of attraction. Hydrogen bonding again. Very, very polar. So as a result, all the hydrogen ions do not completely leave the fluorine ions. So it does not ionize completely. So hydrogen fluoride is an example of a weak acid. All binary acids are strong except hydrogen fluoride. So you're having hydrogen chloride, you're having hydrogen sulfide in our second example. Those are examples of strong acids. And an example, this year's WAEC exam, they said give examples of strong acids. So what could they have done? Pick binary acids and you give them as examples, except hydrogen fluoride. That is a weak acid. So like I said, we'll be discussing number 2 last because I promise we'll be discussing types of oxides. So let's see. The next one is displacing a weaker acid. So I guess I'll say Roman figure 3 first. Displacing a weaker acid from a salt using a stronger acid. This reaction is basically called a double decomposition reaction. So what happens now is that you have a salt and you have an acid. When they react, they are going to exchange radicals. That is the meaning of double decomposition. So I guess I have to write it. It is some call it double decomposition, while some others call it double displacement. Reaction. Oh, I haven't added reaction. So that's what happens. Again, I'm placing this one as a headline. Why? Because when you say double decomposition, it just means they are exchanging radicals. Now you have to follow the fine prints here, the words specifically. It does not say just a weak acid. It says a weaker acid. Soon we'll be discussing pH, but it says a weaker acid. So while we have strong acids and we have weak acids, in strong acids, some are still stronger than others. An example, tetraoxosulfate 6 is a strong acid. Hydrochloric acid is a strong acid. Yet, tetraoxosulfate 6 is stronger than hydrochloric acid. So you can see they are both strong, but some are stronger than others. So that means that if you have a salt that was made from hydrochloric acid and you add tetraoxosulfate 6 to that solution, tetraoxosulfate 6 will be able to displace hydrochloric acid from that solution and you are making an acid. So in the end, the idea becomes, why are you using one acid to manufacture another acid? The simple answer becomes, it is based on need. And now you can make more meaning from the fact that we have different type of chemicals in terms of quantity of production. We have fine chemicals and we have heavy chemicals. You can see why sulfuric acid is a heavy chemical, because it's used a lot in manufacturing other acids and other substances. As you are going to see, uses of acids, which I guess you can have a lot of. So that is the idea. Use a stronger acid to displace a weaker acid. So what I'm going to do now is, I know tetraoxosulfate 6, again, you trying to create your own examples. I know tetraoxosulfate 6 is a very strong acid, and it is stronger than hydrochloric acid. It is stronger than hydrochloric acid, and it is stronger than triazoonitrate 5 acid. So what does that mean? I can use tetraoxosulfate 6 to displace them out of their own salt. And what is their own salt? Remember, how do you get a salt? A metal displaces hydrogen from the acid. So that means when I get, again, it's good to understand this concept because later you'll be dealing with dissociation. We have discussed a little bit, but when salts dissociate, what will be their effect on litmus? This is an idea that you can easily use. You can know the acid they come from and know the base they come from, and you can know their effects on litmus. This will be discussed later. So, how do you get a salt? It is by taking the acid and displacing hydrogen and replacing with a metal. So that means that if I wanted to get a salt of triazoonitrate 5 acid, all I needed to do was remove the hydrogen and replace with a metal. So if I have sodium triazoonitrate, that means this is a salt of triazoonitrate 5 acid. You can see the radical NO3. then the metal has replaced the hydrogen. That's a sort of triazole nitric 5 acid. When that reacts with sulfuric acid, remember we said it is double decomposition. What's double decomposition? They exchange radicals. We explained something similar in neutralization. So the point is that when this dissolves in a solution, you get sodium ion and triazole nitrate 5 ion. Then here you get hydrogen ion and sulfate ion. Double decomposition, they swap radicals. So the negative from here takes the positive from here, and the positive from here takes the negative from here. So you get something like this. This goes to this, and this goes to this. So now you are going to have HNO3 plus, remember it can't be NaSO4, it becomes Na2SO4. Again, here it is easy to get. Na is plus 1, SO4 is 2. So when you swap them, you get Na2SO4. Again, refer back to my previous videos of how to get the formula of compounds. So what do you see? We have used sulfuric acid to manufacture nitric acid. A stronger acid is displacing a weaker acid from its salt. So I'm going to leave that to you. Again, you can have a safe bet. Pick weak acids, pick their salts. They use a stronger acid to displace the weak acid from its own salt. An example, a safe bet. What are examples of weak acids? Organic acids. So if I know an organic acid as, which is one of the most popular, acetic acid, how do I get a salt? This is the removable or replaceable hydrogen. I simply take it out and replace it with a metal. So when that reacts with a strong acid, because it's a weak acid now, that means any strong acid can do the displacement. React with HCl. HCl is going to displace the weak acid from here. So what happens? Again, it splits up into double decomposition. So sodium takes chlorine and the ethanoate ion takes up hydrogen. That's just an idea, but you can expand on that and work on it. However, if you check out our reaction, it's not balanced. So when I place a 2 here and a 2 here, that equation becomes balanced. So that is one method. If you even move further, as you are going to be seeing contact process later in chemistry, contact process involves some say 4 stages, some can expand it to 5, but they all remain the same. It involves some stages. And in contact process, you are trying to manufacture sulfuric acid as your end game. But even in the production, you still use sulfuric acid in one of the stages. That shows you how important sulfuric acid is in the world of chemistry. Again, heavy chemicals. So that's the idea of manufacturing an acid, using a stronger acid to displace a weaker acid from its salt. And then now we are going to be discussing point number 2, which was dissolving an acid anhydride in water. Now, let's start with this first. When you say the word anhydride, do not mix it up with the word anhydrous. Anhydrous means it is dry. Hydrous or hydrated, oh, there's water. Anhydrous, there's no water, it is dry. Anhydride, remember, when hydrogen combines with a compound, with another element, that is called a hydride or anhydride. An example, we have just spoken about binary acids. It is just, for the first example we had hydrogen and chlorine. Only 2 elements combined together, one of them is hydrogen. That is a hydride. The one which is on screen right now, hydrogen and sulfur, just 2 elements and one is hydrogen. That is a hydride. So when hydrogen combines with one other element, that is a hydride. What's the popular hydride that we know? Water, H2O, just hydrogen and oxygen. That's a hydride. So when you talk about hydride, you are referring to hydrogen. So when you now say anhydride, it means there is no hydrogen. That is the simple meaning. There is no hydrogen. So what does that mean? When you now say acid anhydride, you are simply saying an acid which does not have a hydrogen. That's a layman's way of defining it. An acid which has no hydrogen. So it is now you are having H2SO4, but there is no hydrogen. What do you have left? It's like SO4. So that SO4 without hydrogen can be referred to, although not correct, just trying to develop an example here, as an acid anhydride. So always take note, trying to create a difference. What anhydride is and what anhydrous is. They look similar and people tend to think they are the same, but they are very different. So an acid anhydride is an oxide which dissolves in water to give or produce an acid. And that is the main definition. And now, from what you just described about anhydrides, you can now see that the purpose of dissolving it in water is actually for it to be able to get the hydrogen which it requires. So remember, an acid anhydride has to be an oxide, not just any oxide. It has to be a non-metallic oxide. This will help us when we're not discussing type of oxides. It has to be a non-metallic oxide. Dissolve it in water and it gives you an acid or produces an acid. Now we have, again, we have different types of anhydrides. We have what we call the mixed anhydride. Mixed anhydride, when they dissolve in water, they give you two different kind of acids. As you are going to see again, that was a question that came out this year. You have an example is NO2. NO2, which you can say nitrogen dioxide. When it dissolves in water, it doesn't give you just one acid, it gives you two forms of acids. So in that case, some call it mixed anhydride because it gives you two different kind of acids. So, but generally, the main point is that a non-metallic oxide, when dissolved in water, gives you an acid that is called an acid anhydride. And as a result, they can also be called acidic oxides, which is why when you go, you can get various definitions of this. These various definitions, it's not that they are wrong, but they are different facets of the same thing. So let's see an example. Let's just put it and note it for now. An acid, to spell it properly, an acid anhydride is an acidic oxide. We are going to be discussing oxide very soon. So now, an example of acid anhydrides in action. You have sulfur 4 oxide reacting with or combining with water. As you possibly will see later, this is a step in contact process, like I just mentioned. This gives you H2SO3. not H2SO4. Take note of the difference. H2SO4, that's tetraoxosulfate 4, but in this case will be called trioxosulfate. You have to calculate for the oxidation number to know what sulfur is in this equation. And if you check that, I think it's tetraoxosulfate 6, and this will be trioxosulfate 4, calculating the oxidation number. Another example is carbon dioxide dissolving in water. This gives you a weak acid called carbonic acid. Now, again, this brings you back to when you are told about pollutants, and you are told things like, oh, these pollutants, when they get into air, they cause soil pollution, they cause air pollution. Carbon dioxide and sulfur oxide. That's why I use these two examples. How? You are told that when carbon dioxide gets into air, because there's water vapor in the air, the carbon dioxide dissolves in water and it gives you a weak acid. So when it comes down as part of rain, that acid gets into the soil and that makes the soil not suitable for planting. And as a result, what do? You have to neutralize that soil. Takes us back to neutralization. So that is the concept of acid anhydrides. Remember, they are also called acidic oxides. They are much more acid anhydrides, but I guess these two examples will suffice. But just so I don't leave it, like I said, we have mixed anhydrides. Why? Because they give two acids. You can see in this case, it just gave one acid. But now, when you have something like nitrogen oxide reacting with, dissolving in water, that gives you two and not just one acid. So you can see, this is exactly what happens, and that's why it's called mixed anhydride. Gives you two forms of acids. Now what will happen is, I'm going to leave this one for you to actually balance. I guess you can take care of it. So in this case, remember, it is not just a regular acid anhydride, but it's called a mixed acid anhydride. It gives two forms of acids. Just had to point this out. But the idea remains that it is giving two forms of acids, but it is still producing acids. That makes it an acid anhydride. Alright, so that's how you produce acids, the three methods. But now, because I'm mentioning anhydrides, I'm mentioning oxides, that now takes us to what we call types of oxides. Well, do let me know, once you balance this chemical equation, let me know what the solution is. So, type of oxides, we have four main types of oxides. Again, you can see the idea. What's an oxide? It's an element combined with oxygen. That's why, depending on who you talk to, H2O, hydrogen combined with oxygen, just hydrogen, that can be called a hydride. Oxygen combined with hydrogen, oxygen, that can be called an oxide. So some persons tell you water is an oxide of hydrogen, and some others tell you water is a hydride of oxygen. You can see concepts. All right, types of oxides. First, we have acidic oxides. Why are they called acidic? Basically, they behave as an acid. And because they behave as an acid, what happens is that they react with bases to give or to produce salt and water. They just have the properties of acids generally. So these same oxides, when they dissolve in water, well, automatically, when they are dissolved in water, remember, they have already produced acids. So their effect now is that they will turn blue litmus red. And as a result, these same oxides, because they have acidic nature, you are told that they turn damp blue litmus red. If it is a dry litmus, it does nothing. But if it is damp, it turns it red. Why? Or in some cases pink, like in the case of carbonic acid. Why? It is simply because since it is damp, that dampness means there is water. That water is able to dissolve the gas, giving you the weak acid. The weak acid turns blue litmus to the color we are talking about, which is red. So that is the idea. Acidic oxide reacts with bases to give salt and water. They turn blue litmus red. And then, we just spoke about it. Acidic oxides are also called acid anhydrides. So the point remains, they dissolve in water to give acids. So those are acidic oxides. And how do you get acidic oxides? Acidic oxides have to be non-metallic oxide. Well, I'm going to group them before I give specific examples. The next one is neutral oxides. As the name literally says, they are neutral. They are neither acidic nor are they basic. So what does that mean? If it was acidic, it would react with base to give salt and water. If it was basic, it would react with acid to give salt and water. But it is neutral. It is not acidic. It is not base. So therefore, it does not react with acid. It does not react with bases. If it was an acid, it would turn blue litmus red. If it was a base, it would turn red litmus blue. But it is neutral, so it does not have any effect on litmus. So that is the idea. And then mostly, they are practically insoluble in water. But the point I want to make, when you are talking about acidic oxides and neutral oxides, they are oxides of non-metals. I'll say it again. They are oxides of non-metals. So when you may be giving questions, you are giving oxides and you are told to pick which of them are acidic, which of them are neutral and all that. When you get such things, look for the non-metals. They are either going to be acidic or they are going to be neutral. So for acidic oxides, we have already given examples under acid anhydrides. I guess I can also add another example of an acidic oxide that was not mentioned there. Nitrogen pentoxide, or somebody can say dinitrogen pentoxide. In fact, this is the proper acid anhydride of nitric acid. When you dissolve this in water, it actually gives you HNO3, which is nitric acid. For neutral oxides, one of the most popular examples is carbon monoxide. Produced from the incomplete combustion of carbon. Possibly soon we'll be discussing carbon and its compounds. But that's how it is produced. From the incomplete combustion of carbon. Use generators or use things that use fuels, fossil fuels. You get it from there, incomplete combustion. That is a neutral oxide. It does not have any effect on litmus. It is insoluble in water and all that. It is neutral. So it does not react with acid, it does not react with base. Another example is N2O and NO. These are the most popular ones. Dinitrogen oxide, and then you have nitrogen oxide. So you can see, don't mix them up. Nitrogen pentoxide is an acidic oxide. Nitrogen dioxide, which is NO2, is an acidic oxide. But carbon dioxide is an acidic oxide. But carbon monoxide, dinitrogen oxide, and nitrogen oxide, they are all neutral oxides. But you can see what they're having in common. They are all oxides. That means non-metals combining with oxygen. They are all non-metallic oxides. So whether acidic or neutral, they are going to be non-metallic oxides. For the next two, they are going to be metallic oxides. So the first one we have are basic oxides. From what we have already discussed under acidic oxides, I believe this one becomes clear. Basic oxides, they react with acids to give salt and water. We were speaking about it in the previous video on how to develop your own neutralization reaction. That's for basic oxides. And then obviously again, they will dissolve in water to give bases. But something you must note here, not all of them are soluble in water. Some are insoluble. So in such cases, do not expect them to be dissolved in water to give their bases. So in such cases, such bases, there are different ways of manufacturing them. So if the oxide is soluble in water, then it can be dissolved to give a base. And that takes us back where we'll be discussing bases soon. So I guess it takes us forward. That when you have bases, so basic oxides are basically bases anyways. So when you have bases, when they are soluble in water, they are called alkalis. So all alkalis are bases, but not all bases are alkalis or alkalis, depending on how you prefer to pronounce it. So it is, if it is soluble in water, it will dissolve and give the base. What is the base? The hydroxide. All right. So for your basic oxides, you can list a whole lot. Remember again, they are metallic oxides. However, what I like to do is, this is Roman figure 4. We have amphoteric oxides. For amphoteric oxides, these oxides, they have both acidic and basic properties. So what does that mean? For basic oxides, when they meet acids, they react to give salt and water. But when they meet bases, nothing happens. They don't react. For acidic oxides, when they meet bases, they react to give salt and water. But when they meet acids, nothing happens. For neutral oxide, it does not matter what they meet. Whether they meet acids or bases, nothing happens. But for amphoteric, they now have the properties of acids and bases. So what does that mean? When they meet acids, they react to give salt and water. When they meet bases, they also react to give salts, but mostly complex salts. And that's what happens. So they react with both acids and bases. The next logical question becomes, acidic oxides turns blue litmus red. Neutral oxides have no effect on litmus. Basic oxides, obviously, are going to turn red litmus blue. So amphoteric oxides, what will be their effects on litmus? Well, most of them are insoluble in water anyways, so they may not have any effect on litmus. But when they form their salts, depending on the level of dissociation, will have effects on litmus. But the oxide themselves, they don't have a pronounced effect on litmus because they have both properties, basically. So that is the idea. They react to both acids and they react to bases. And now remember, for the first two, acidic and neutral, they are non-metallic oxides. But for the last two, basic and amphoteric, they are metallic oxides. So that means when you're looking for basic oxides, it has to be the oxide of a metal. Looking for amphoteric oxides, it has to be the oxide of a metal. So what are amphoteric oxides? Well, the most popular ones, you have this beryllium oxide, you have aluminium oxide, you have zinc oxide. Zinc is a transition metal, so you may have to say zinc 2 oxide. I guess people get the picture when you say zinc oxide. You have tin oxide, and you have lead oxide. These are the most popular amphoteric oxides. So once you're able to list out these ones, automatically, most likely every other metal you're going to be mentioning, they are going to be basic oxides. Well, as you can see, their oxides, even their hydroxides, behave in exactly the same way. So zinc hydroxide is also amphoteric. Tin hydroxide, also amphoteric. Lead hydroxide, amphoteric, and so on. Hydroxide, that is not their basis. These are just their oxides. They are oxides, but they behave as bases. So, having gotten this one out of the way, we are now asked to list basic oxides. Well, list as many metals as you can mention and their oxides. So you have sodium oxide. You remember their proper formulas. You have magnesium oxide. You have calcium oxide. Just to mention a few. You can add potassium oxide. You can add lithium oxide, and so on and so forth. Those ones are now basic oxides. So that is for acids. Next, we'll be discussing bases, then move on to pH, then salts, or we can move on to salts before pH. But for now, go through this. If you have questions, always remember to put in your questions and I'll get around to them.